much, but I think it's good to get the astronomy 111 level description before we step it up much. So, any questions? Yes?
Why is the universe born?
Why is the universe born? Because of inflation. Because of inflation. First of all, I would argue it's not born. But second of all, in other words, why doesn't it have a nice cool geometry, right? We think the answer to that is inflation when the universe was about 10 to the minus 36 seconds old or thereabouts. A cosmological constant that's much larger than the present one in the universe would have caused it to exponentially inflate in size. And as is actually shown in my notes that I posted, that will imply that even if the universe was very far from flat before inflation began, after inflation, it would be very, very close to flat. And while this wasn't appreciated a few decades ago, it pretty much has to be, because you can show that without dark energy, without any kind of cosmological constant, if the universe is not flat, then it gets further away from flatness as time goes on. If you turn it around, as you go back towards the Big Bang, the universe gets closer and closer to being flat. And furthermore, if the universe is anywhere close to flat today, if the critical density, if the density parameter is anywhere close to 1 today, it had to be amazingly close to 1, close to the time of the Big Bang. And in fact, you can show that without any dark energy, a universe which had, say, a density parameter of 2 right now would be much younger. It would have already, that would be a closed universe without dark energy that would fall back on itself and have a big crunch. It would not be anywhere close to 13.8 billion years old. So it turns out that there's this flatness problem that needed to be explained anyway, and inflation is the explanation for that. So inflationary cosmology implies that the universe is flat, and our observations confirm that the universe is flat, is what it comes down to. So this is another idea of that. There was a mission before the WMAP and Planck missions called Boomerang, which was a balloon mission that flew in Antarctica high enough to make measurements of the cosmic microwave background anisotropes. So here's real data from Boomerang about the hot and cold spots. And then you can also make simulations of what the pattern would look like in a flat universe, in a positively curved universe, and a negatively curved universe. So here's a simulation of the pattern in a flat universe. Here's a simulation of a pattern in a positively curved universe with a certain value of the R0, the radius of the current radius of the universe. Here's one for negative curvature. And so this is showing this idea that the hot spots would look bigger in a positively curved universe, smaller in a negatively curved universe. Here's the simulation for a flat universe. You tell me which one is a better match just by eye to the Boomerang data. Clearly it's the flat one. Even your eye can tell you that. Now, of course, if it was slightly curved, it would be harder to tell just by eye, but you can do a more detailed analysis. And so what we want to do is, I guess what I'm going to do first is to jump ahead a little bit and talk about, so the temperatures that we see in different directions of the sky represents a function of position on the celestial sphere of the observed temperature of the cosmic microwave background radiation. So in other words, it's a function of theta and phi. You just put the spherical coordinates angles on the celestial sphere, call them theta and phi. Any function on a sphere can be written as a sum of what kinds of functions?
Straight harmonics.
Straight harmonics, right. Spherical harmonics, right.
Spherical Bessel functions.
Spherical Bessel functions, right. Right. Well,
complete orthogonal basis.
yeah. So the spherical harmonics are a complete orthonormal basis onto which you can expand any function on the sphere. The temperature of the cosmic microwave background radiation is a function on a sphere, namely the celestial sphere. So we can expand that pattern of hot and cold spots into a sum of spherical harmonics. And that's what I meant when I was talking before about the power spectrum and so forth. When we say the typical size of the hot spots is 1 degree, what we mean is when you look at the expansion in terms of spherical harmonics, the strongest coefficients, the biggest coefficients are ones that correspond to variations on an angular scale that are typically of about 1 degree in size. So here's a reminder, we saw these before when we were talking about stellar oscillations, right, stellar pulsations and so forth, helioseismology and all that, here are the spherical harmonics of order L equals 6, and remember that L tells you the number of nodal lines on the surface, the total number of nodal lines, and M tells you how many go through the poles. So L equals 6, M equals 0 has 6 nodal lines, none of which are in longitude. They're all in latitude because none go through the poles. Here's L equals 6, M equals 3. Here's L equals 6, M equals 6. If L equals 6 and M equals 6, then they all go through the poles, and so there's no latitude lines. They're all longitude nodal lines, so to speak. Now, here's the nicest, so okay, so just for fun, all right, so let's go nuts here. This is in French, but in any case, here's L equals 1, M equals 1 color-coded. So red and blue for plus and minus, which is convenient because our pattern of hot and cold spots is red and blue too. So here's L equals 1, M equals 0, so then there's only a node on the equator because none of them go through the poles. Here's L equals 1, M equals minus 1. Oh, this one's minus 1, this is plus 1. That just shifts 90 degrees in longitude when you do that. Because remember that one of them is a cosine of phi and the other is a sine of phi. And so they're just shifted by 90 degrees. L equals 2, M equals 0, L equals 2, M equals 1, L equals 2, M equals 2. And then just for kicks, L equals 36, I think it says there, M equals 0. L equals 36, M equals 12. L equals 36, M equals 24. L equals 6, M equals 36. So the typical angular scale as measured at the center of the sphere gets smaller and smaller as the order, the value of L, gets higher and higher. So in other words, if you think of writing the pattern of hot and cold spots in terms of spherical harmonics, then if you get the strongest contributions from L's around 36, then you'll see a pattern which has hot and cold spots on the order of these kinds of sizes. That's the idea. Questions, Mark? I never thought of that before. How can I never thought of that?
I thought that's what he actually meant.
I meant question, comma, Mark.
What's up, why, is there such a color gradient? Like,
Oh, that's artificial.
That's
It would be
artificial.
smooth. It should be smooth.
okay.
Yeah, it should be perfectly smooth because they're continuous functions. Yeah, it's just that I don't know, they have a limited color palette or something like that. But you're absolutely right. It should be a smooth variation. It should not be like, there should not be like lines like that.
Wait, so,
So like a
it
contour line.
should be like
It should be a continuous gradation in color that you're seeing there. So those are like contour plots, basically, where they just color in all the same shade when the value is between this value and that value, that sort of thing. You know? So this is I really like this. It's the best example I've ever seen of showing how spherical harmonics can be used to build any function on a sphere. So any mathematical function defined on the surface of a sphere can be obtained by adding together spherical harmonics. For example, here is a map of the topography of Earth's surface, altitude, plus and minus above sea level, color-coded to represent the altitude of each location. So dark blue is deep, and the reds and whites and greens are above sea level. So this is minus 10,000 something. I'm not sure what the units are. If they're smart, it's meters. I'm not sure though. 30,000 meters, is that reasonable? That would be 30 kilometers. No, it can't be. It must be 30,000 feet. That's probably more reasonable for the deepest parts of the ocean. U.S. and yeah, right. Yeah, that's weird. Anyway, high altitudes, low altitudes, and strangely enough, the oceans, they're not counting the water, just the ocean, the surface below it. Strangely enough, it's shocking, I know, but the oceans typically lie below sea level, and the continents typically lie above sea level. Here is what? What is this? That's the Himalayas, right? Yeah, and so those have very high altitudes. That's why they're like this color. Okay? Here is the best approximation that you get using spherical harmonics of orders L equals 0, 1, 2, 3, 4, 5, 6. So, in other words, if I restrict myself, I'm only allowed to use spherical harmonics with L equals 2. So there's 5 of them I get to add together in that case. Then here is the best fit to the Earth's topography based only on using them. In other words, remember that to calculate them, you do an integral. You integrate the function against the spherical harmonics, right? Just like with Fourier coefficients. Function times, a sine gives you the sine coefficients. Functions times a cosine gives you the cosine coefficients. With the Legendre polynomials, where we've gotten rid of any azimuthal variation, there's that integral of function of theta, PL of cosine theta, sine theta, d theta tells you what the coefficients are, times of 1 over something or whatever. Same deal, except a little more complicated with the spherical harmonics. So basically, you take the function times the spherical harmonic and integrate it over the sphere to give you the coefficients. You do that in each of these cases in order to figure out what the coefficients are, then you add the spherical harmonics with those coefficients, and the resulting surface is the best approximation you get for that set of spherical harmonics. So if we're only allowed to use L equals 1, well, you're not going to get a very good fit because L equals 1, you've only got 0, minus 1, and plus 1 for M, and L equals 1 has very large scale variations in angle on the surface, so you don't expect to get a great fit. On the other hand, you do basically well, here's the Pacific Ocean and here's not the Pacific Ocean. You can get kind of that level of detail, right? When you put higher and higher orders, you kind of do better. But what you really want to do, of course, is now combine them together. In other words, don't just use L equals 0 ones or L equals 1 ones or L equals 2 ones. Combine. Use all the spherical harmonics up to L equals 6. Use all the spherical harmonics up to L equals 12. To get a perfect match, you have to use all the spherical harmonics up to L equals infinity in principle, right? Principle.
So what function would you use?
You would do this on a computer. You'd have a digitized map of the Earth's elevation, and you do the integral numerically. Yeah, you'd have to do it numerically, because I don't know about you, but I can't imagine writing down literally an analytical function right. So no, you use a digital version, and then you integrate that numerically with digitized spherical harmonics. You have no choice. So here is Earth's actual topography. Here, if you take all the spherical harmonics between L equals 0 and L equals 6, and add them together with the right coefficients, the best values of the coefficients, this is what you get, right? So you start to, we're talking here, right? I mean, you're starting to see some Australia. You're starting to see some South America action happening here. Here's some North America action. There's some mountains showing up there, right? Okay, and hello, Africish, right?
I don't think there's a face in Africa.
No, I never noticed that before. Oh, yeah.
Oh, so happy.
Oh, I know, yeah. Hi, I'm Africa. Yes. Hakuna Matata, maybe, right? Is it so? Okay. Here is going all the way to L equals 16. Hey, look. Definitely getting some Himalaya action
Starting
there.
to get a little bit of like Rocky Mountain action.
Getting some Rocky Mountain action, as a matter of fact, yep.
Like the
Why,
trench of
we're making some Greenland, what's that?
The trench of the Pacific Ocean.
Yeah, you got some Pacific Ocean trench happening, right?
It looks like
Yeah.
light action.
What's that?
The Pacific Ocean kind of looks like the light lamp from A Christmas Story.
Oh, it does! Right, yes. It does kind of, or Italy.
Or Italy.
Or Italy.
That too.
But then any leg looks like Italy, vice versa, so, right? Here's out to L equals 36. So, not perfect, but we're starting to be pretty good here, right? When you go all the way out to L equals 36. Definitely some Himalayas happening here, Greenland, Rocky Mountains, Andes, all that kind of good stuff, right? Pretty cool. Yeah. So this is the nicest demonstration I've seen of the fact that you can add spherical harmonics together and duplicate any function that you like. They stopped at 36, but if you kept going, you'd get closer and closer to this, is what it comes down to.
For your specifically, does this actually give us any information, or is it just a cool demonstration?
It gives us information because, for example, and here I took the slide out. It gives us information because you can produce then a plot of coefficient, basically what amounts to coefficient squared versus L values, or the sum of the squares of the coefficients versus L values. And if you do that, if you tend to peak at low values of L, that's telling you on some level the surface has mostly large-scale fluctuations in elevation. If you had a planet which didn't have very many really pointy, small, high altitude or low altitude regions, if it just had kind of big continent-sized undulations in height and depth, then its power spectrum, a plot of coefficient squared versus L, would peak at low values of L and fall very rapidly at large values of L. On the other hand, if you had a surface which didn't have any big plateaus, it didn't have continents and oceans, you had a surface that was covered with lots of small mountains everywhere. Then you would expect not much power at low values of L, which correspond to small scales of variation, large scales of variation. You would have it peaking up at large values of L, which correspond to rapid fluctuations with distance along the surface. And so, I should, in the break, put it back in. You can learn things about, like, I took a slide out that shows the power spectra for Mars and Venus and Earth, right? And so, and I didn't want to talk about it, but I should have left in there. I didn't realize that he was going to ask a question like that. But it's an excellent question. So, so it gets better and better the more spherical harmonics you add. When we do this on the celestial sphere, as we will see, you can make you can calculate what the power spectrum should look like for the universe is this much dark matter, this much ordinary matter, this much dark energy. And you can compare that to the actual power spectrum. And we get a beautiful match for particular values of dark energy contribution, dark matter contribution, ordinary baryonic matter contribution. That's how we know the fractions of dark matter, dark energy, and baryonic matter. It's from models that best match the expansion of the fluctuations in temperature in the cosmic microwave background radiation in terms of an expansion in terms of spherical harmonics. That's what it comes down to. That's what they're doing, is seeing what model gives the best fit in terms of how it would look in terms of the expansion in terms of spherical harmonics. So, break time!
Break. Picnic time.
What's that?
The religion department picnic.
Oh, right, yes. Oh, even more reason to be recording this, yes.